Hello students. So now we are moving to the next topic, Fourier transform. So first of all, what is Fourier transform? Fourier transform can be represented as ft. Both Fourier series and Fourier transform are the mathematical tools for representing signals and frequency domain. Fourier series are mainly used in periodic signals and Fourier transforms are used in aperiodic signals. So now let us look into the general formula of Fourier transform. The Fourier transform of f of x in the integral minus infinity to plus infinity can be represented as f of s equal to Fourier transform of f of x equal to integral minus infinity to plus infinity f of x into e raised to minus x sx dx is called Fourier transform of f of x. And also the function f of x defined as 1 by 2 pi integral minus infinity to plus infinity f of s e raised to minus I sx ds is called inverse Fourier transform of f of s or inversion formula. And these are the basic formula of the Fourier transform and inverse Fourier transform. And Fourier sine transform. The function f of s is defined by fs of s integral 0 to infinity f of x sine sx dx is called Fourier sine transform of f of x in integral 0 less than x less than infinity. And also the function f of x is defined by f of x equal to 2 by pi integral 0 to infinity fs of s sine sx dx is called inverse Fourier sine transform of f of s. And another one is Fourier cosine transform. The function fc of s defined by fc of s equal to integral 0 to infinity f of x cos sx dx in integral in limit 0 to infinity. Also the function f of x is defined by f of x equal to 2 by pi integral 0 to infinity fc of s cos sx dx is called inverse Fourier cosine transform. So here we look the Fourier general formula of Fourier transform, inverse Fourier transform and Fourier cosine transform and inverse Fourier cosine transform and Fourier sine transform and inverse Fourier transform. Now these are the properties of Fourier transform. The first one is linear property or linear theorem, and second one is shifting property, and third one is change of scale property, and fourth one is modulation theorem. So first one is linear property. If capital F of s and g of s are the Fourier transform of f of x and g of s respectively. Here there is a correction. Sorry for the mistake. This is supposed to be g of x, not g of s. So the linear property becomes Fourier transform of a into f of x plus b into g of x equal to a into Fourier transform of s plus b into g of s, and where a and b are the constant. We know that the general formula for Fourier transform can be written as f of s equal to integral minus infinity to plus infinity f of x e raised to minus I sx dx and g of s equal to integral minus infinity to plus infinity g of x e raised to I sx dx. So the in linear property Fourier transform of a into f of x plus b into g of x can be written as integral minus infinity to plus infinity a into f of x plus b into g of x into e raised to minus x dx. We seen that e raised to minus x is common in f of s and g of s. So that can be written as a into integral minus infinity to plus infinity f of x e raised to I sx dx plus b into integral minus infinity to plus infinity g of x e raised to is x dx. We know that integral minus infinity to plus infinity f of x e raised to Isx dx can be written as f of s, and integral minus infinity to plus infinity g of x e raised to ix dx can be written as capital G of s. So the equation becomes a into f of s plus b into g of s. So we proved the linear property. Now we move to the another property is shifting property. If f of s is the complex Fourier transform of f of x, then shifting property can be written as Fourier transform of f into x minus a equal to e raised to is a into f of s. So we know that the Fourier transform of f of x can be written as f of s integral minus infinity to plus infinity f of x e raised to isx dx. Therefore, Fourier transform of f of x minus a can be written as by replacing x as x minus a, that is integral minus infinity plus infinity f of x minus a into e raised to isx dx by substituting x minus a equal to t. So, x can be written as t plus a by taking derivative dx equal to dt. So, the equation becomes integral minus infinity plus infinity f of t e raised to minus s t plus a dt. So, equal to, we know that e raised to I raised to m into a raised to n equal to a raised to m plus n. So, e raised to is into t plus a can be written as e raised to ist into e raised to isa dt. So, by taking outside e raised to isa, we can get that e raised to isa into integral minus infinity plus infinity f of t e raised to ist dt. So, integral minus infinity plus infinity f of t e raised to ist dt can be written as Fourier transform of f of s, that is e raised to minus isa into f of s. So, we prove. So, the other properties we'll discuss later.